everyone. Welcome back to the lectures on Introduction to Multi-Agent Systems. In the previous lecture, we saw that the leader-follower controllability of an interconnected system depends a lot on the eigenvalues and the eigenvectors of a submatrix associated with the Laplacian matrix. However, how do these properties relate to the topology of the network? In general, the question is, what role does the topology of the network play in leader-follower controllability? Should we make the network highly connected, meaning a complete graph, or should we make it minimally connected, like a spanning tree? In today's lecture, we'll try to answer these questions. So let's get started. So as before, we start with a group of n agents. Those n agents are governed by the Laplacian flows. And out of those n agents, we pick just one agent, which now acts as the leader. So now the job of the leader is to control the rest of the agents in the network, who are known as the followers. So again, the leader is subjected to some external inputs. And through this leader, the external inputs are trying to desirably alter the states of the followers in the network, known as the leader-follower controllability. However, the interesting question that we till now have not answered is that, what role does connectivity of the network play in this entire process? Is it better that a network is highly connected, or rather, we want the network to be very sparsely connected? In order to answer that question, let us directly look at the most dense network that we can think of, an all-to-all network. Before we look at the example, let us first formally state the objective. Consider a group of n agents split as n-1 followers and one leader. The leader was subjected to external input, to an external input U, and is trying to steer the followers. So the question that we'll try to answer is, what role does the topology of the network play in this process? And the first case, as we mentioned before, that we look at is an all-to-all graph, or a complete graph. So we'll analyze whether a complete graph is leader-follower controllable or not. Again, we start with a set of n agents. For a network with n agents, we know the following things. the degree of each node is equal to n minus 1. Hence, the Laplacian matrix takes the following form. All the diagonal entries, since the out degree is n minus 1 for each node, all the diagonal entries are simply n minus 1, and the rest of the entries will be minus 1. Why? Because this is a complete graph, and there exists an edge between every pair of nodes. This way. This Laplacian can be written a bit more in a concise way in this manner. N times In minus the matrix, an n cross n matrix with all entries being equal to 1. So this is what the Laplacian looks like for a complete graph. In our leader-follower framework, which matrix we look at? Let's see. For that, we bring in this matrix here, and we say xf dot and xl dot is now equal to let us partition the network first. We know that the last node, the nth node, is always our leader. Hence, this entire row vector becomes equal to 0, and this also is set as being equal to 0. We have here xf, xl plus 0 times u. So to be a bit more precise, let's make these all zeros. So now we are trying to look at the properties of the LFF matrix. If you remember, what do we want? So we discussed it in the previous lecture that this matrix represented as LFF must satisfy two conditions for controllability. Just to quickly remind you, first condition, all the eigenvalues must be distinct. In order to write the second property, let us denote this column vector as LFL, the n-1 cross 1 matrix. Then the eigenvectors must not be orthogonal to the vector LFL. So can you please pause the video here and try to tell me, or try to figure it out by yourself. What does this LFL look like? We have written only 2 of the entries, but obviously you can easily see that every other entry must also be equal to -1. Hence, LFL, in the case of an all-to-all graph, is simply equal to this particular vector. And what is its dimension? It will have n minus 1 entries. Okay. So now we need to test if these conditions hold or not. Let us start by calculating the spectrum of LFF. Interestingly, when we try to calculate the spectrum of the matrix LFF, we realize that eigenvalues are given as follows. One of the eigenvalue, so let's look at our, just remind you of the form here. LFF again has n minus 1 along the diagonals, and the off-diagonal entries are all equal to minus 1. In such a case, the eigenvalues are, one of the eigenvalues is equal to 1, and the rest of the eigenvalues are actually equal to n. In fact, the eigenvalue n is repeated n minus 2 times. So what did the first condition for controllability say? It said that the eigenvalues of LFF must be distinct. But what we see here is it always has repeated eigenvalue for any system with n greater than 2. It always has repeated eigenvalues. What does it mean? This clearly implies that a complete graph is not leader-follower controllable. Which is quite a surprising result. We allowed now the leader to be connected to each and every agent or each and every follower in the network. Despite of that, what we see is the leader still cannot control all the followers in the network. So somehow too much of connectivity has in fact hampered the performance of the system. Now let us look at the other extreme of this graph. This was a complete graph. So the other extreme, or another kind of a graph which would have minimal connectivity, is a path graph. So let's see how things turn out for the case of a path graph. A path graph would take the following form. Let us consider the network shown in this figure. This is a path graph, as you can see, and the node in green is our leader node, and the rest of the nodes are the followers. So what does the Laplacian matrix look like in this case? Node number 1 is connected only to the second node. Node number 2 is connected to both 1 and 3. And node 3, this is 0. And node 3 is connected to 2 and 4. Again, node number 4 is connected only to node number 3. Now, when I want to write it in the leader-follower dynamics, it takes the following form. So now, again, there are a few things that we already know. The last one is the leader here. So all of its entries turn out to be we make it 0. Then we have xf, xl plus 0 times u. This is our setup. So in this formulation, this is a matrix or submatrix LFF. So now we are interested in figuring out whether LFF satisfies all the properties which are discussed here. First, all of its eigenvalues must be distinct. Second, its eigenvectors must not be orthogonal to LFL. So what does LFL look like in this case? LFL has all of the entries as 0 except for the last entry, which is equal to -1. So now let us compute what are the eigenvalues. The eigenvalues of this system are given 3.25, 1.55, and 1.99, or close to 2. So meaning the first test is cleared. All the eigenvalues are distinct. So now we move on to the next test. We'll check whether its eigenvalues are orthogonal or not to LFL given by this. Let's highlight LFL. This is a LFL. So what are the eigenvectors? The eigenvectors are given by -0.55, -1.25, and 1. -0.8, 0.44, and 1. And the last one is given by 2.25, 1.8, and again 1. And we have to check orthogonality with LFL, which in the case of path graph is given by this. The last entry is equal to -1. For our particular graph, it will have 3 entries, as shown here. Then it follows. So let's mark. Suppose this is equal to V1, this is V2, and this is V3. Then it follows very clearly that Vi transpose LFL is equal to -1 for every I belonging to 1, 2, and 3, which implies that Vi is, let's highlight it, or the eigenvectors of LFF are not orthogonal to LFL, meaning the path graph has now cleared both the tests. Surprisingly, what we got is the path graph which is connected in the least way which is possible for a network to be connected turns out to be controllable, whereas a complete graph is not controllable, meaning connectivity in fact adversely affects the controllability. So here we have shown in the case of an example, if the students are interested in figuring out the exact calculations for a path graph, let me add the reference here. This material is borrowed from the paper. Let me write it. The controllability of nearest neighbor interconnections. And the author is a detailed proof of why the path graph is controllable is mentioned in this reference. And all of the points discussed in this paper, in this topic on controllability, is borrowed from this paper. So please take a look at this paper for more details. However, now what we do is summarize our results. The first thing that we conclude out of this is connectivity adversely affects leader follower controllability, which implies that it is unlikely for a graph with increased connectivity to be controllable. What does this mean? It means that suppose we start with some graph, G, and now we keep on adding edges to it. Then we are actually reducing its chances of being controllable. As the number of edges increases, it tends to be or tends towards uncontrollability. Similarly, now as the size of a network, so this is yet another interesting result, which says that as the size of a network increases, the probability of finding a controllable graph reduces. Suppose these contain, each of these are simply graphs of size, say, for example, 10. This is G1, G2, and they have 10 nodes. And this is, suppose we add a larger set, which is the set of all graphs of size 10. Then, whatever is the probability of finding a controllable graph, let us now compare it with yet another system where we now change this to 15. And again, we have all these graphs, G1, G2, and so on. The chances of finding a controllable graph is much less in this set as compared to this. This is what it implies, which is a very important and interesting property of how controllability actually weakens as we increase the connectivity within a network. So with this interesting result, we will close the topic on controllability of networks. In the next lecture, we'll move towards studying dynamical systems a little bit more, and we'll also study about some tools which can be used for nonlinear systems. Thank you.